Hi students, it's your professor Dr. Mink, and welcome to another exciting lecture for Comp Sci 3. In this lecture, we're going to be discussing lists. Lists are linear collections like queues and stacks, but they're a little more flexible because you can add and remove elements, not just from the ends. You can add and remove elements from the middle, which makes lists much more versatile than a stack or a queue. However, stacks and queues um, have their applications. So let's take a closer look. You can probably see the similarities in these abstract data type conversations. We're going to talk about the specific ADT, in this case, a list, and how it fits in with types of list collections, and then how we solve problems with lists, how we implement lists. If you remember, the stack was implemented with an array, the stack was implemented with a linked list, etc. And then we will compare various implementations and the pros and cons of those. As I mentioned in the previous slide, a list is a linear collection. So in that way, it's similar to a stack or a queue, but we can add or remove elements at either end or anywhere in the middle of the list. And we're going to examine three types of list collections: ordered list, unordered list, and then indexed lists. So in an ordered list, the elements determine where they're stored in the list. So in an ordered list, there's some inherent characteristics or characteristic of the elements that determines where they go in the list. So it may be a list of names that are stored in alphabetical order. It may be numeric values that are sorted in ascending or descending order. Here we're looking at a graphic depiction of an ordered list that appears to be storing integers. And uh, you can see that they're stored in ascending order from the front of the list to the rear of the list. So the front of the list in this example holds 12. The rear of the list holds 81. And they are increasing in an ascending way. So if we wanted to add 54 to this list, it would have to go in between 49 and 57. I think that's pretty straightforward. You should not have any problems with this concept. It's when we get into unordered list, which gets a little bit more complex. So in an ordered list, the order is based upon some characteristic of the elements in the list. In an unordered list, there is an order, but it's not based on characteristics. So it's not a series of names that are stored alphabetically, ascending or descending. So the user of the list determines the order of the elements. And a new element, regardless of its characteristic, can be put on the front, in the middle, which is basically after or before a particular element in the list, which is an interesting differentiation. Or you can put at the end of the list. So you can put a new element in a list in front of an existing element or behind an existing element or at the front or at the end. I'm not artistic enough to modify this nice graphic depiction of an unordered list, but I would probably put some characteristics on those boxes. So in this, you can still see the front of the list, the rear of the list, and we can add an element at the front, at the rear, or somewhere in between the front and the rear. And it would not go there based upon a characteristic of the element, like ascending, descending, sorting, etc. In an index list, elements are referenced by their indexed position on the list, just like the indexes used in an array. So similar to the unordered list, there is no relationship among the characteristics of the elements, and the user determines the order. Every time a change is made to an index list, the indexes are updated. So if you insert an element in the middle of an index list, all the indexes are updated each time an insertion, an extraction, anything happens. So here you can see basically the same graphic with some very slight changes. What are they? You in the third row. Oh, never mind. So here we see the indexes. And so the initial state of this index list is that it's storing 8 elements, and their indexes, as you would have guessed, zero-based numbering system, 0 through 7. So if we were to add an element to the front of the list, the element stored at index 0 would then become 1, 1 would become 2, and we would then go from a list of 8 to 9 elements. And the new element added to the front of the list would be stored at index 0. Likewise, if we were to add an element at the end of this list, okay, it would assume index 8. If we add an element in the middle and in the graphic depiction in front of you, it shows adding an element between index 3 and 4. That element would become index 4, and 4 would become 5, 5 would become 6, etc., etc., etc. So hopefully you're starting to see the differences between ordered, unordered, and indexed lists. And obviously, we're going to implement each of these list types in code. There are list classes in the Java API, and those list classes primarily support indexed lists and, to a degree, unordered lists. However, the Java API does not have any classes that directly implement an ordered list. The array list and linked list classes both implement the list sub E interface, and that E is a generic data type. And you're going to see that, and you're going to see, we've already seen T. T, E, and U are the same. However, people tend to use T for type, E for element, V for value, and K for key. But they are generic data types. Here are some of the operations, the methods from the list E interface. We have add E element, adds an element to the end of the list. Add with two parameters, an integer index and then an element, inserts an element at the specific index. Get, and then an integer index parameter returns the element at the specific index. Remove, int index removes the element. Remove, and then a generic object parameter removes the first occurrence of that specified object. It's different than the index. It will look for the object, not the index location. And then set an index, and second parameter is an element. Replaces the element at the specified index with the new element, parameter number 2, in the method call. And then size returns the number of elements in the list. Obviously, I like this next example because it uses the context of a college program of study or degree and the courses necessary to complete the degree. And we're going to use an unordered list to manage the courses necessary to fulfill a certain degree. So the course class will represent a course which may or may not have already been taken. The program of study manages a list of course objects, and the list is stored for later use using serialization, which we'll get to. Now we're going to take a look at a program that uses a list to manage a set of objects. And so we have this course class that implements serializable. This is the serializable interface, and it creates an object that can be saved using serialization. And there's no methods in the serializable interface. It's used simply to indicate that the object may be converted to a serialized representation. So what is a serialized representation? It is a JVM independent format for saving linked lists and array lists. So this list at the very end of this program is going to be saved, and we'll see, you'll see that. So the course has a prefix, and a string prefix, integer number, string title, and a string grade. So, and then we're going to use these objects to develop a program of study. Now, program of study also implements the serializable interface and the iterable interface. Now, I'm disappointed that the way the author presents these topics is not necessarily linear. Iterable is the next big topic in this class. So let's just say it makes lists easier to manage in sequential for loop type situations. I'm not going to go too deep into iterable right now because we're going to spend an entire week on the iterable interface. So this program of study, this class program of study implements serializable, that special format, JVM independent format, and the iterable interface. So it creates a list of courses, and we have various methods: add a course, find a course, add a course after
And the parameters are we pass a course target, and then a course new course is the second parameter, and it will add that course after the target course, and it will renumber the indexes after that automatically. Replace, and we're using all of these in the driver program toString. And then here is the iterator used to return the list. And we'll get into that in more detail without muddying the waters. So here we have this POS tester driver program, and we create a program of a study object named POS, and then we call add course, and we're adding a new course, and this course prefix number, I can't remember the name of the last two prefix number, title, and grade. Yeah, I couldn't remember what they were called. So we're going to add these courses to the list, and I've got this set up. So we can look at this with some breakpoints. I'll run this in debug mode. So there we come to our first course, and if we look at POS, we have a list, and it has, let me see if I can get this over here for us. We've already added, darn it, I can't get this over. We've already added CSE 111, Introduction to Programming. I know that's off the screen right now. I'm sorry about that. I just can't get this size so we can see that. So if we walk past that, we add a second course, and now we have 0, CSE 111, and now we've got this other course, ARC 305, and then I'll add some more courses, and this will just simply, so now we've added 1, 2, 3, 4, 5 courses. They are stored in the list, the linked list, at 0, 1, 2, 3, and 4. So now we're going to find CSE 240, and we're going to assign it to an object reference variable for a course called ARCH. I'm assuming that means architecture, because I teach CSE 240 and we do go over some architecture. So, and now we're going to add, after ARCH, which is pointing to the course CSE 240 Computer Organization, we're going to add a new course, CSE 223 Computer Science 2, and we're actually going to add a grade of F. That's what you're going to get if you don't pay attention. Sorry. Couldn't help myself. I hope none of you get an A. I'm sorry, none of you get an F. So here we go. Let's see. CSE 220, 240 was at 3. And at 4 was Theater 201. And so now if I look at CSE 23 is now at 4, and Theater is now at 5. Lists are really nice. You could not have done that with a stack or a queue. So POS find, we're going to find that Theater course, and when we added it, we did not add a grade to it. We did not initialize the variable for a grade. Some of them have grades, some of them don't. So now we're going to call the setGrade method, and we're going to assign a value of A minus. That's a string. We're going to replace the German course. Okay, so we're going to do POS fine, German 210. I think that might have been the first or second one. Whoops. Sorry. No, it might have been maybe the third. Yeah, there it is. It's the third element or object in this list. We're going to use POS find, create a new object reference variable theater, assign it to that, set the grade of A. Then we're going to find German 210, and we're going to replace German with a new course. So the German is the third element. And if we look, it's gone. It's replaced. And now we're going to print POS, and we're also going to save it in a serialized format. That's the JVM independent. So go to output. We'll see it's the entire thing printed. And this save POS program of study. If I go to my files, there it is, program of study. So I hope you enjoyed this. Lists are great. I'm sorry. Lists are better than, lists are more flexible than queues and stacks. I shouldn't say great, better, no superlatives, but they are more flexible in that you can add items and delete items from the interior. You don't have to work at one end or both ends. One more note about serialization. Any class whose objects will be saved to a file are tagged with the serializable interface. And that enables us to create that file that we just saw, and that file can be used to access those, or I should say, that file contains object data that is JVM, Java Virtual Machine independent. So it is across platforms, if you will, if you want to consider the JVM a platform. And here we have diagrams showing the relationship between the program of study class, the course class, and of course the linked list that we implemented to store a program of study. That brings us to the Josephus problem. Now, the way the author presents the Josephus problem is very different than the way it was presented to me the first time I saw this in, I can't remember which class I saw it in, but it might have been this, the equivalent of this class way back when. The way it was presented to me was as the Josephus permutation. And it's a theoretical problem related to a certain counting game. And the way I remember it is people are standing in a circle waiting to be executed. Yeah, that's probably why the author didn't present it that way. And counting begins at a certain point in the circle and then proceeds around the circle in a specified direction, counterclockwise or clockwise. And after a specified number of people are skipped, the next person is executed. And the procedure is repeated in the same direction with the remaining people, starting with the next person, going in the same direction and skipping the same number of people until only one person remains and is freed. So the problem Given the number of people, the starting point, the direction, and the number to be skipped is to choose the correct position in the initial circle to avoid being executed. So that's a little bit more memorable for me than the way the author has it presented here. It's the same thing. Start with a particular element, and every ith element is removed, and processing continues until there's only one element left. So same thing, removal, execution. These are crazy times in our world, so I understand why the author would not want to use the execution example, but that's the one that I was used, and I guess I just used it again. But it stuck with me, it really did. So there you go. Now the moment you've been waiting for, the Josephus permutation or problem implemented with a Java program that utilizes a list. And so this is all in one file. So in our main, num people, skip, target index, list is a new array list of strings, scanner, in, and I added this. The file that you're going to download from the author doesn't have this in there. I didn't like the way the output looked, so I made a few slight minimal changes. We're going to solicit the number of soldiers from the keyboard. We're going to solicit the skip number, if you will. Then we're going to use a for loop to add soldiers. And we start to count at 1, and we go up to less than or equal number of people. So we don't have a soldier 0 in there. And the order is, and then while, and I changed this a little bit, list size is greater than 1. It will continue to remove a target index and print that the soldier, their number, and eliminate it. I'm making this politically correct. It's not executed anymore. And then when we're done, we'll have a list size of 1. Okay. And that will have an element at index 0. Because this is an index list, we implement it with an array list. So we'll print out the survivor is. So if I run this, let's just say, I don't know, 15 soldiers, and the skip number is 9. Okay, who wants to guess which soldier is the last man standing? I guess I should say the last person standing. Yes, we do have male and female soldiers in this scenario. So soldier 7 is the last soldier standing, or the survivor, if you will. Of course, I would take this program, I'd put it in a project, and play around with it so you understand what's happening here. If you wanted to run this with a breakpoint and watch the list, I could put a breakpoint right here, run it in debug mode. What I would prefer to do, is use a smaller list. So let's say 5 soldiers and the number is 2. So we've hit that breakpoint. If we come down here, oh, there's my list, sorry. We've got soldier, you can't see it, it's off the screen. Got 1, 2, 3, 4, 5 soldiers, and it will just arbitrarily, okay, now it removed soldier 3, now it removed oh, hold on. Remove soldier number 1, 5, and it looks like, oops, that must be done. Soldier 4 was the survivor. Okay, you know what to do with the file, right? I don't have to tell you that for the 72nd time today.
Now let's implement our own list collection. These operations are common to all types of lists, so we'll have access to them. Operations that are particular to an ordered list are add, which adds an element to the list. Operations particular to an unordered list, add to front, add to rear, add after, and you can guess how those work. We're about to take a look at a ordered list implemented as a linked list. And I'm going to give you a peek at your next assignment, which is Programming Project 15.10, where I ask you to write an implementation of the linked ordered list class and put the driver program that we've been using in front of it. So here's a couple screen prints with a lot of really valuable information, if you know what I mean. So I'm running this program, my version of it, in debug mode, and I'm stepping into it. And so here I've entered 1, which calls the method add in the linked order list interface. And you'll notice I add, and this is all based upon a list of strings. So I add will, W-I-L-L. And then I add Yuval. And then I add Xavier. Now remember, this is an ordered list. So they're added to the list based upon some characteristic. And here's the major hint. And if you're not watching the lectures, you're going to miss this. And everyone who asks me, how did you compare the objects to determine where they went in the list? I'm going to say, you're guilty as charged of not listening, watching the lecture. Sorry. We're going to use comparable, which you're going to have to take a look at. Yes. So here is a peek at the add method. If the element is not an instance of comparable, and strings are instances of comparable, they can be compared. Okay. So it throws a non-comparable exception. And if not, it creates a new generic comparable named comparable element, and it is assigned element. Now element is what is entered as the next element, in this case string, to be added to the list. We've got linear node, excuse me, got the linear node class in there. And this is the logic which determines where, because this is an ordered list implementation, where those values, I'm sorry, that object, that string object will go. So notice I've added Will, Yuval, and Xavier. You don't have to go past the first character to compare those as less than, greater than, or equal to. Let's take another look at the memory, the variables at this point in the state of this program. Here we are at the same breakpoint. So it's a state snapshot of the program. And you can see William is at the head and Yuval is at the tail. And if you recall, the order in which I added them was William, Yuval, and then Xavier. So I'll give you one guess where Xavier is, if William's at the head and Yuval's at the tail. So if we look at the head, right, it's a linear node. It has an element and it has a link to the next element. And then the tail has a link to the next element, which is null. Okay. Now, if I were to click on the plus of next in the head, I would see the next node. And guess what is there? Okay. There's some huge hints here for you. Of course, if you're not paying attention or you're not watching my video lectures, then, well, you know what happens. Bad things. So I'm going to show you this running live next. Here we are where we just left off, except we're live. And so here you could see the tail, and if I were to page up, you'll see the tail, and the tail holds a null next, and the element it holds is the string Yuval. Here's the head. Okay. Oops, I'm sorry. The head holds a next, right? And the element is Will. And then next, right? Next holds Yuval, and the element is Xavier. So we have Will in node 1. Actually, it's node 0, but in the head. Will and a linear node next. And then in next, we have Xavier and a linear node next, which is Yuval, and a linear node next, which is null. So we have a list of 3 objects right now. So just to give you an idea of what you're going to need to do. I mean, here is the, this is the driver program that it's got the same interface. I'll give you a screen print of it. Linear node, we've been using that all along. Linked list, we've been using. Here is what you need to implement. Linked ordered list. Okay? It really only has one additional element. Linked order list, right? Implements list ADT, which implements linear node and linked list, right? You know the routine, right? If I go to linked list, right? Implements list ADT. I'm sorry, linked order list implements linked list. So this is a major hint for programming problem 15.10, which is now officially assigned. And if you miss this lecture, then it's unofficially assigned, or you missed it. Whatever. You get it, right? Obviously, I'm going to put a rubric
This is really complex compared to what we've been doing in the past, and I'm undecided whether or not I'm going to have you also implement an unordered list, which I believe is linked unordered list class is 15.11. I'm thinking about that. I don't know, we'll see how the rest of my day goes. Just kidding. Now I'm going to show you the program running, and I've got some elements of the IDE screen hidden, if you will. So here's my I'll go through every file that I have in the source packages. This is my main. I just called it P1510, and it's your driver program that implements the menu. I'm just going to click on each file, and you can take a look at the screen. These are really great hints, as a matter of fact. Okay, there's linear node, linked list, and you could, here's the file that is really the bulk of the assignment, and you could see got list ADT, ordered list. You have all these. You should have all these exceptions already. These are just 3 exceptions. If you don't have them, ping me. I'm sure you do from a previous assignment. So anyway, I'm going to run this now. So you could see this thing in action. So the main menu system, which we've been using, this is a variation of what we've been using all along. If you want to make this horizontal so that it's all on one line, list menu selections, I think we did that for the link queue or one of the other previous assignments. That's fine. So let me add an element to the linked ordered list, and we'll pick one in the middle of the alphabet, Mary. Okay, so Mary, if I choose 3, is now at the head, and if I choose display, it shows me 1 element. So if I were to add an element, James, okay, now James is at the head of the list. If I choose display, 2 elements in the list. If I add an element, Nancy, where do you think Nancy is? Well, Nancy's now at the tail. If I choose let's add Karen. Karen was inserted appropriately in the list. This is an ascending list of strings. And so let's add Aaron. You could probably guess where Aaron is going to go. So the new head is Aaron. List. If I remove an element, let's remove Aaron. Okay. And now James is back at the head of the list. That should be sufficient. If you have any questions, obviously ping me and we'll get those questions answered. There's some really, really significant hints, head starts in what I just showed you. Use it wisely.
You might have guessed what we're going to do next. We're going to implement a list using an array as the underlying structure. So, since elements can be added anywhere in the list, we're not going to be able to avoid shifting elements because of the way an array stores data in linear fashion. So, if we insert an element or delete an element, all of the indexes behind that, after that, are going to have to be shifted. And the rear is going to have to be shifted, one either positive or negative, depending upon if it's an insertion or a deletion. Let's take a look right now.
Next, we're going to take a look at an array, a list that is based on an array. Everything else is the same. I've got a driver program. We're using the generic T-type for the elements that we're going to add to the array. I just happen to like using strings as that element, but it could be a float. It could be any other any object we wanted to add to this. So I think for demonstrating the function of the list based upon an array, it's easier to use a simple object like a string. So anyway, and I do have a breakpoint, so I'll be able to show this to you. And by the way, this is officially assignment programming problem 15.8. It's an ordered list implemented with an array. So let's add some names to this. I will add Henry, and then we'll add Jane, H-I-J. Let's add Earl, and then we'll add Jane, and then you got the obligatory Aaron, right? Oops. And let's take a look at what we have here. So here is our list. Our rear is at 4. And notice they are not in the order that I entered them. I think it was Henry, Jane, Earl, and Aaron was the Henry, Earl, Jane, and then Aaron. So obviously we're in an ordered list. And so if I were to remove, let's remove Henry. Now notice Jane is at index 3. Okay, the rear is at 4. Somewhere buried in there is a size. So let's remove Henry and see what happens. Let's remove Aaron. See what happens to Earl at 1, Henry, and Jane. And this is a necessity without using the links. This is, if you're using an array, you're going to have to shift all the elements in the array after the event. So if the event takes place at element 0, element 1, 2, 3, etc., all have to get shifted, because you can't have an element removed without shifting the indexes. You would not have an ordered list. You would not be able to manage that. So anyway, let's Let's proceed past that breakpoint, and let's now remove Aaron. Aaron's been removed. Let's look at our list. Earl was stored at index 0. He's now, stored at index 1. He's now at 0. Henry, Jane, etc. And if we add elements, they will be handled appropriately. So I'm going to remove this breakpoint. So let's now see our first element is Earl. I'm still at that breakpoint, sorry. If I want to display, it will tell me what I have displayed. If I want to look at my last element is Jane, and I think that's it. So take a look at what we have here. This is really really the file you're going to be adding the most to. You've got that, you've got array ordered list, right? You've got, we've been using list ADT, okay? The only thing this adds, ordered list ADT, is the add. I'm sure you have all these exceptions. Yeah, I think I gave them to you in the files. So yes, you're going to have to implement a list using an array, and you will duplicate, emulate what I have here. Use this menu system, add all these menus, and I'll put a rubric in the timeline for Canvas. And of course, if you have any questions, don't hesitate to ask me.
Hopefully, that look at a list implemented with an array helps you to understand the nuances between a linked list and an array-based list, and all the data management and movement that takes place when using an array as the underlying structure for a list because of the array indexing system. You insert an item in the middle of the list, and then everything with an index equal to or higher to the insertion point has to be moved. So, in my opinion, and I think many developers share this opinion, a classic linked list is the obvious choice for implementing a list collection. We've looked at the linear node class, which was introduced earlier in this lecture, and it's just a very efficient way of doing this. You hold the element, the linear node, a linear node object has the element, whatever it is, and the linkage to the next element. Head and tail references are maintained, and you have an integer to hold the count of the list.
So, to sum up our discussion on lists, I'd like to go back to the linked list class, which implements list ADT and the iterable interfaces. And I'd like you to go over this class with a fine-tooth comb. It's well developed. It is the easiest and most efficient solution to a linked list. A list that can be ordered or unordered. We haven't spent a lot of time talking about unordered lists because really they only have an add, and you add the new item not based on its characteristics but to the end of the list, and it becomes the tail. So I'd like you to focus your time on the linked list class, and all of the methods and the structure of the head, the tail, mod count, the concept of iterator, which we're going to drill down on in the next lecture. It allows us to cast an object as an iterator, and that provides access to has next, next, remove, etc. So there are a couple more slides in this deck, but they deal with JavaFX. And the problem is we have 3 professors at the college who teach the prerequisite course. And I know they don't, at least one of them doesn't delve into the GUI JavaFX because that person is a Swing proponent, and I don't believe they implement Swing and GUI in CSC 122. So it will be an optional FYI kind of topic that we'll cover next.
As I mentioned, these last few slides in the deck deal with JavaFX, which is the API for graphical user interfaces that Java has adopted. It replaces Swing, and the JavaFX API adds some constructs for lists, and they're added primarily to provide GUI support or graphical user interface views of lists. And they also provide wrappers for existing Java collections. And these are defined in javafx.collections package. First up is the observable list interface, and classes that implement this interface are given access to change listeners to track changes to the list in the GUI. So in other words, they will listen for an event if an element in the list is changed in any way. And so here, when we have a list of courses, we can develop a observable list that will put a change listener on that as it's represented in the GUI. And we also have the list view, which will provide a GUI representation of the list. I believe checkbox, list box, combo box all are included in that list view option. When you have an observable list, you can provide a comparator for sorting decisions. And so this is the code that would create an observable list of my courses, and then it would create the sortable comparator for sorting those courses. And I believe, my friends, that is, yes, this is the last topic in the list lecture module. And I would just want you to take away from this that lists, abstract data type that can be implemented with various data structures, linked list and array are the 2 most common implementations for lists. And you have ordered list, which are the sequence of the elements in the list are ordered based upon the characteristics, whether it's numeric or it's Unicode sorting, ascending, descending, etc. And an unordered list is a much more simplified list in which the sequence in which elements are added to the list are the way they reside in the list. Pretty straightforward, I think. Of course, there's going to be questions, and you have two thought-provoking assignments on lists. So thanks for watching. Have a great day. Of course, if you have any questions, you know what to do and how to get a hold of me. Take care.